Hello, everyone. My name is Eric, and I'm here to talk to you about integration by parts. So this will be sort of like the intro to integration by parts. So this is the 101, starting from ground zero. If you just started discussing integration by parts in your class, this is a good starting point. I do plan on building off this with other videos to have more comprehensive understanding of integration by parts, but we're going to start with the basics here. So the first thing I want to do is discuss where integration by parts comes from. And this by no means is going to be a formal derivation. But just like U substitution and other methods of integration, this is essentially the reverse, the inverse of a derivative rule. So integration by parts is the inverse of the what is this? Product rule for derivatives. So if I have f times g, which, by the way, I do want to say that I'm going to be using f of x and g of x as my two functions instead of u and v, because I will sometimes get these two things confused. But keep in mind that in your class, you'll likely see the two functions as like u and v. Okay, anyway, back on track. If I have a product of two functions and I take its derivative, then I will have the derivative of the first times the second plus the first times the derivative of the second. Gotta move this thing. All right. Cool. So let's do a little bit of simple algebra. I'll have my derivative. So we've got f times g. Excuse my extremely large and terrible handwriting. I'm going to subtract the f prime, or what did I choose to do? Okay, I chose to, I'm just going to stick to my notes so I don't get confused later. I chose to subtract this one over to the other side. So I've got f prime of x, g of x. All right. I'm going to go ahead and integrate both sides. And maybe I'll find a way to do this where I don't have to rewrite everything again. Yes. No, come on, please. We'll just leave that there. Let's not worry. I'm going to integrate both sides, take the antiderivative of both sides. So keep in mind that like that is the thing that I'm integrating over on the left-hand side, which I'm going to go ahead and split up. So let's see here. We've got integral d dx f of x, g of x, dx minus integral. So keep in mind that because these two things are a difference, I can choose to split it into two integrals, which I'm sure you guys already know, but I just want to be explicit in my explanation. G prime of x, all right, dx is equal to f prime of x, g of x, dx. All right, cool. So this is essentially I just need to, all right, there we are. This is essentially the integration by parts rule, because if you look at this now, once again, this is why it's not a formal derivation. I'm just going to sort of hand wave this, where I have a derivative with respect to x, and then I'm integrating with respect to x. Someone with a PhD in math might be a little upset that we just say, hey, well, this is the same thing as f of x times g of x. That is essentially what it is, but there's maybe some caveats that need to be said there for a formal derivation, which we're just going to ignore. Okay, so let's look at this. And I want to look at the right-hand side because this is, generally speaking, what you're going to be given in a integration by parts problem. You're going to be given the left-hand side, you're going to be given a integral, which is a product of two functions, and you are going to have to designate one of them to be a derivative and the other to be the original function or a different original function. So you're going to have to designate one to be f prime and one to be g so that you can then use this formula to find the antiderivative. The reason we might do this is say that for whatever reason, f prime of x times g of x is not an integral we know how to take. But if we were to take f times g prime of x and integrate that and take the antiderivative of that, that is something that we would feel more comfortable with. And this does happen from time to time. So on occasion, you have this sort of product inside of an integral and you say, I don't really know how to deal with that. Let's go ahead and use integration by parts to figure it out. Go away. Leave me alone. Okay. Where is she here? Oh boy. Dude, sorry, there was an update to this like whiteboard software and I'm struggling. Okay, so I'm gonna go with the first example that I have here, which is x times e to the x dx. Now, hopefully those of you who are watching this video, this integration by parts video, I have to assume that you already know what the derivative and the integral of e to the x is. So I'm just going to assume that for those of you who don't know, it's just itself, e to the x. You take the derivative or the antiderivative, it's still e to the x. Okay. So what I want to consider is I want to name my g of x and my f prime of x. And I've only got two options. So there's only two possibilities. And a lot of times you will have a case where one works and one does not. Very rarely, both of them will work, but generally speaking, you'll get a situation where you have to choose correctly. And what I would say is that trial and error is expected. Don't expect to get all of these right immediately. Don't expect to guess right the first time for all of your problems. Just be aware that you may make the wrong choice. And if you make the wrong choice, what ends up happening is that this integral is basically impossible for you to solve. So that's a good indicator like, hey, I should have made the other choice. A little piece of advice I would give is that g of x is going to be differentiated. So if you have something that will become simpler when differentiated, and then the other thing doesn't become that much more complex when integrated, that's a good way to go. So for example, I want to call g of x just the piece x. So I'm saying this is my g of x, and therefore e of x, or I'm sorry, e to the x would be my f prime. Okay. So the reason I'm doing that is because g prime is super simple. G prime of x is just equal to 1. Isn't that nice? And f of x, as discussed earlier, is just e to the x. All right, so I managed to make something much simpler through differentiating, while the other piece did not gain any sort of complexity when taking the antiderivative. All right, cool. So here is the formula then. I need to take f times g, so x times e to the x. And then I need to subtract f, which is just, let's see, e to the x, times g prime of x, which is just 1. Okay. And then this is a very easy integral. As discussed earlier, the antiderivative of e to the x is just e to the x. Plus a constant, of course. There you go. So this is a a pretty easy example. This could have easily been done also if e to the x instead was replaced by a trig function, because trig functions, once again, they don't gain a whole lot of complexity when you integrate them, or some of them. If it was sine and cosine, if it was like tangent, then we have to talk because things get a little weird from there. But if it's just sine or cosine, it's very easy to take the antiderivative of that. And then once again, x is just going to turn into 1 if we take the derivative. All right, cool. Let's go ahead and try another example that's a little bit more complex. All right, so now I'm going to have almost identical thing here, but the x squared is going to cause a little bit of a wrinkle that is going to make things a little bit more complex for us, a lot of bit more complex, as we'll find. So I want to do the same sort of thing where I know that x squared, it's not going to go to a constant, but it is going to go to a linear function when I take its derivative, right? So it's quadratic now, and then it will turn into x over 2, which is a little bit simpler. And then, of course, e to the x doesn't really change no matter what I do to it. So I'm just going to go ahead and say I want, sorry, let me see. What was my notes? What are my notes again? Right. Okay, so no, yeah. G of x is going to be equal to x squared, and then f prime of x is equal to e to the x. Okay, so that means g prime uh, is equal to x over 2, and f of x is equal to e to the x. All right. So using our formula that we have, we can say that this integral is equal to x squared e to the x minus the integral, which is f times g prime of x. So that's x over 2, that's g prime, and then e to the x, that's f. Okay, dx. Now, here is the problem. This is not easier for us to solve. I mean, like maybe it's a little bit easier, but it's not exactly easier. So we can't solve that, but we do know that this is a product of two functions inside an integral, which means we can apply integration by parts again. Oh no. Don't know what that was about. We can apply integration by parts again. I'm going to go ahead and rewrite this to look like this. No, wrong. 1/2. 1/2. Okay. So luckily, x times e to the x is an integral we already did integration by parts on, so we do know what it's equal to. But keep in mind that this sort of thing can happen. I did this explicitly because I wanted to show you that this is possible. There are times where you have to take integration by parts multiple times to get to an integral that you can actually do. So we're just going to shortcut this because x times e to the x is something we've already done. Minus 1/2. And then remember, we ended up with x times e to the x minus e to the x plus c. And there you have it. Obviously you can distribute the negative 1/2 in and whatnot. But I'm not going to bother. I think we've made our point here. What I will say is keep in mind that you do want to distribute this negative sign when you actually evaluate for a second time. I think a lot of the time students do not bother grouping the second integration by parts in parentheses and therefore miss the fact that that negative sign out in front negates everything inside, right? It would negate like that, and like that, right? So you want to be careful there because that does happen. I see that mistake pretty often among students. All right. So let's see here. I'm going to have one more example to kind of throw another wrinkle into this and just kind of show you what's possible. So I'm going to have the integral x times ln of x dx. Okay, so once again, I want to bring up the choice of what is f prime and what is g, because it might not be necessarily as obvious for this one. So I said, hey, a good rule of thumb is if you have something that goes to a constant that becomes simpler if you take its derivative, you should do that. But I also had the caveat of the other thing needs to not get that much more complicated when you integrate it. So I'm looking at this and I say, okay, x clearly will get simpler if I take its derivative. It will turn into 1. But then I have to integrate the natural log of x, which unless you have that memorized or you have the form of it in the back of your book that you're staring at, may not be that simple for you. And even if it is, I'm pretty sure that it creates an integral that is kind of bananas as well. So we don't really want to deal with that. You know what? I take it back. That integral might make sense. I don't actually have the uh, integral of the natural log form memorized. I'd have to do it. So we're not going to worry about that. But unfortunately, it means that our a choice of g of x being x and f prime of x being natural log of x gets a little messy, gets a little complicated. Once again, like if you're very comfortable taking the integral of natural log of x, good for you. You can just do it that way. But I think there is a simpler way to do this. So I am going to go ahead and swap the order. And this is, once again, what you would do if you had made that choice and you said, hey, I can't really do this integral still. I've hit a wall. You would go back and you would say, all right, let's go ahead and make the other choice. So I'm just going to switch. I'm just going to say, well, natural log of x will be my g of x, and f prime of x will be my x will be my f prime of x. Easy for me to say. So let's just kind of see what happens here. So g prime of x, once again, I'm making the assumption that you know what this derivative is. But for those of you who don't know, it's 1 over x. And f of x would be equal to x squared over 2. All right, cool. So let's go ahead and apply that to our formula. So we'll have x squared ln x over 2 minus the integral, which will be 2 x squared over 2 times 1 over x dx. So something really nice happens to us here where we have some simplifying happening in this integral. So we end up with just x over 2 in the integral, which we can pretty easily solve. Hope you guys follow that. It's just the integral of x is x over 2 or x prime or x squared over 2, and there's already an over 2, a 1/2 piece there, so it's now over 4. And so I just wanted to throw this one at you to show you that sometimes you do need to make oddball choices for what your g and what your f prime is. It's not as simple as, oh, that's a linear piece, or this is a power rule. So I know if I keep taking its derivative, it'll go to 1, or some other constant eventually. It's not always that simple. Sometimes you have to make weird choices. And I do want to point out that our weird choice came when we had natural log of x as our other function. If we have, once again, sine or cosine, we probably don't need to make any weird choices. If we have e to the x, we probably don't have to make any weird choices. This is, of course, assuming that our other piece is a polynomial or a power of x. But for natural log of x, we did have to make a strange choice. So that's something you may want to keep in mind. These rules, these are not hard and fast rules. These are just kind of like guidelines of like, hey, when you see this product inside your integral, here's some things you can expect. And I think that does it for me today. There will be another video, hopefully it's already up in the series, talking about what happens when you don't have things simplifying no matter how many times you take do the integration by parts rule. But we'll get to that in the next video. So take care, you guys. See ya.